Well, good morning. This is Scott Jarman, the 2020 chapter president of the local chapter of the Association of Energy Engineers for Austin and San Antonio. We have a great program set up for today, and we'll get that kicked off in just a couple of minutes. Just make a couple of quick announcements. Last week, we stood up our new website and sent out invitations from that website, so our emails will look a little bit different. So check your spam filters and your junk mailbox if those emails are going there. They should be coming from an email address, communications@txaee.org. And we're going to try to use this website to manage our membership and post meeting notices and documents, backup documents for those meetings. It has some work to be done, but it is stood up and operating. So bear with us. If there's any suggestions that you have, please let us know, and we'll work on that. Next month we have Scott Casper. He has volunteered to work with us to put together a program on lighting. The specifics are not quite nailed down yet. Scott is with Bracom, and he was referred to us by one of our members, Herb Gantz. So more to come on our next meeting in September. Last month, we had a social hour and had several people on the line on a Zoom meeting, and we talked about several things. Some of it was around the current topics of the day, and the program today will definitely be timely. Look for an invite for a follow-up social hour. The feedback was that we should have another one, and so I'll get the information out on that. And if you're interested and willing to participate, please join in. So without further ado, I would like to introduce Marwa Zatari, the Chief Science Officer at Blue Box Air Technologies. She leads the research efforts there and is very versed in heat exchangers, filters, indoor air quality measurements and management, and how to design and operate buildings for optimal energy efficiency and people efficiency. She has extensive experience in indoor air quality, exposure management, and economic impacts of indoor air pollution. She earned her PhD in architectural and environmental engineering from the University of Texas with a focus on the built environment. She's a distinguished ASHRAE lecturer and a member of several ASHRAE committees. I would like everyone to give a warm welcome to Marwa Zatari. Thanks.
Thank you so much. Hi, everyone. Thank you for having me. I recently moved to Austin. I'm currently in Austin, Texas, and I look forward to meet you in person soon when we can have these meetings, physically or face to face. I'm going to share my screen. So can I do this? Okay. You can see my screen, right?
Yes.
Okay, great. So my presentation today is about HVAC strategies in the age of COVID. Some of these strategies you can use, they apply pre-COVID and also beyond this pandemic. Just give me 1 second. So I do this setup here. So this is the agenda for today. I'm going to summarize for you the most common HVAC strategies from different organizations, including ASHRAE and IFMA and REVA, the European Ventilation Society. I'm going to rank these strategies by cost effectiveness and take a deep dive into 3 topics for today: filtration, coil cleaning, and flush out. And later, I'm going to show you an example of how to run a risk infection model and do cost analysis to do trade-off between different competing strategies. And at the end, I'm going to show you something new I'm actually working on, which is COVID-19 testing. So the first question that we've been dealing with is that, is the virus airborne? And if it's airborne, what are the HVAC strategies? So there are consensus from different organizations. And I put here a summary of them on the bottom of the slide, that the HVAC system is part of the solution and can play an important positive role in mitigating the risk of transmission. From the beginning of this pandemic, we were bombarded with many different strategies. Here you can find some of the more common one. And in the next 2 slides, I'm going to tell you in details about what do we mean by different strategies. But to tell you is, I sit on the ASHRAE Epidemic Task Force, specifically on the commercial team. And even for me, some of these strategies were confusing. And it is true that some of the recommendations are mutually exclusive. Some of them are contradictory even, and some of them are complementary. To give you an example, if you were to open your outside air to have ventilation or dilution, but then you compromise thermal comfort, is that acceptable or not? Like, which one is more important? Because the guidance tell me that I have to increase ventilation as much as possible, but then at the same time, I need to maintain thermal comfort. How do I do that in an existing building? Another one is that if I have outside air pollution, like if there's a fire, or the intake of my building is next to a highway, it's really polluted. Which one is more important? Should I open my outside air as much as possible, or I should take care of the pollution? The last one, which is my favorite example, is that if I have 100% outside air, all my total supply is 100% outside air, then it doesn't make any sense for me to upgrade my filtration, because I will have 0% indoor air that is recirculated through the HVAC system. So that's an example of like mutual exclusive strategies. If I have 100% outside air, it doesn't make sense that I upgrade my filtration to clean return air. So in this presentation, I'm going to show you a lot of these examples and how we can prioritize the different strategies. Like first, a quick overview of the most common strategies. The first one is filtration. And here I am talking about the basic good old particulate filters where we have third-party certification. So absolutely, filters do help to remove the virus. I will show you later in details which efficiency do we need. What we know is that we have basically a terminology, which is MERV, minimum efficiency reported value. This is the way that we refer to our filters. And the residential is a bit different, and also in Europe is different. But this is one of the rating, if you want to know. And then we know that the higher the MERV, the higher the efficiency. And also today the guidance is to use MERV 13 minimum. So they say MERV 13 minimum, MERV 14 preferred. Next we have UV, and the most common is UVC or UVGI. So UV is a proven technology that can disinfect the air, and it was used a lot in hospitals still until today. It was not used in commercial buildings or in residential, at least not as much as intensity as used in the hospitals. So ASHRAE and different organizations said, you can use the technology to disinfect the air. UVC is one of them. And for UV, we have a knowledge how to basically spec it, because we have a standard about UV. How much should be the dose, the output, the depreciation, and other items that we're going to talk later in this presentation. But it's really important is that it needs to be properly designed and maintained. And as you will see later, to properly design it, you need to spend a lot of money. And also another point, which is really important, is that UV might not be the right solution to clean coils. It might be the right solution to disinfect a room while it's not occupied, or upper room, but it's not the right solution to disinfect coils, as I will show you later. Last item on this slide is electronic air cleaners. I don't know if you basically deal with this or you have spec'd this in the past. I put here a link from the ASHRAE website. You can also see on the CDC. There are a lot of concerns about electronic air cleaners. To start, we don't have a standard for electronic air cleaners. They're so confusing. They have many different names, and they work, on more or less the same principle. And none of these technologies have real peer-reviewed journal data or a standard that you can benchmark or you can compare if you have if you have basically the right solution or not. Just gonna check my message. And the CDC, the Center for Disease Control, recently came and said that we don't have these data, so be careful when you spec them. And specifically, they talked about bipolar ionization, is that this is specific technology that have less documented track records. Next, coil cleaning. Should we do coil cleaning? Yes, and this is specific as well to the pandemic. You always need to do coil cleaning. It is in the ASHRAE standard and International Mechanical Code. But what's unique here is that for the pandemic, we're focusing on having to clean the entire depth of the coil or any heat exchanger that you have. Energy recovery ventilation. In ASHRAE today, we say it depends. If you have an energy recovery ventilation that is leaky, either by design or by installation, and there is a whole manual how to do the check, then you need to disable it. Demand control ventilation, and this refers to basically ventilating on demand. Usually it's installing carbon dioxide sensors, and if you have less people, you decrease the ventilation. In this specific context, we say disable this demand control ventilation because, you know, the guidance, you want as much outside air as possible. So if you have sensors, you can, you know, play with it by setting an extremely basically high limit for the sensors or low, depending how you're doing it, or just disabling. So having the no outside air control, just open it basically to as much as your system can support. Flush out, I'm going to talk a little bit about this later. Yes, flushing out indicate that you are getting outside air to your building outside of normal occupancy hours. So if your building open from 8 to 5, you basically get outside air before 8 or after 5. How much and for how long, I will show you later. The last item here is outside air ventilation. So outside air ventilation or dilution, so basically getting outside air into your building. Today, you have to get a minimum outside air per ASHRAE standard 62.1 for commercial or 62.2 for residential. Depending on your city and state, some residential don't have ventilation. But basically, you have to be careful about this, and I will show you later. So the basis of the strategies today is to do very good particulate filtration, MERV 13 is minimum, do coil cleaning, and ensure you have at least the minimum compliant outside air. If you want to go beyond this, you definitely can, if your system can able to maintain thermal comfort conditions, and also if you don't have outside air pollution. And then you need to, you basically consider the cost of energy. I will show you this a little bit later. So in a nutshell, the recommendation revolve around the basics. The basic that will work during a pandemic, that worked before the pandemic and will work beyond this pandemic. The basics of particulate filtration, coil cleaning, and ventilation specifically. So back to the basically the original, where I started this presentation. So obviously these are a lot of strategies. So if you have a limited budget or if you want to start somewhere, how you prioritize these strategies. So here I put here the basically order of effectiveness, cost effectiveness, first on operating cost. So I took the risk of infection and the cost of different strategies first on operating cost, and this is the rank. We start first with source control. Source control is beyond the purview of ASHRAE, beyond the scope. And this is basically, it says source control is basically reducing the strength of the contaminant. In this case, we're talking about COVID. So an example would be wearing masks, doing disinfection, or basically reducing the occupancy in the space. If you're not there, you can get sick. And there is a lot of talk from CDC about the, if symptomatic, stay at home, about having thermal imaging to detect temperature. So this is the source control. The second one is source removal. So this is the second in rank about cost effectiveness. So source removal in this context, we talk about particulate filtration and coil cleaning. And this is, compared to other strategies, is the most cost effective. And last is dilution. And in this context, it's cheaper to buy and operate particulate filter than to basically increase ventilation, and depending on your climate. If you are in Austin, San Antonio, it's hot, it's humid, it's going to cost you a lot of energy, for example, if you just open your outside air to 100%. And the key is that how to do the trade-off, how to prioritize the strategies and how to pick a trade-off. Before I go there, I want to basically run through a few slides about particulate filtration, coil cleaning, and flush out. I'm going to take this deep dive before I show you the results of the risk infection model, and then we can have a discussion. So the first one is about particulate filtration. So from the beginning of the pandemic, there was a lot of talk, like, do existing particulate filter work? Do we need to upgrade? Do we need the HEPA level or basically the hospital grade? And the answer to this lies in understanding the characteristic of the virus specific. And it has to do with basically the size, and also since we humans are that source of this virus, the characteristic of what we emit. So the first thing, and you might have seen this all over, in this picture here, you can see the size of the virus. So it's 120 nanometer in diameter, or 0.12 micrometer, 0.12 micrometer. To give you an example, or to put things into perspective, the diameter of a human hair, basically human hair one, is 50 micrometer. And here we're talking about 0.12 micrometer. And I compare it here to PM10, and this big giant, basically black round thing. And then this is PM2.5. PM2.5 refer to particulate matter less than 2.5 micron. PM10 less than 10 micron. So when you see this, the size of the virus so small, this is not very positive news. But then we also understand that the virus doesn't exist naked in nature. It's basically an enveloped RNA virus, and basically it latches on a particulate matter, or it exists in a fluid, like you see here on the right-hand side of the picture, making its size bigger. And this is where the good news come. Before I share the next, I just want to make sure that you know what we mean by minimum efficiency reported value. I saw someone put the link in the chat. So today in the United States, specifically for commercial, automotive, healthcare, we rate the particulate filter using this rating from ASHRAE standard 52.2. It's called minimum efficiency reported value MERV. And what it does is that today you can ask your basically particulate manufacturer or supplier to give you this data. It's very common for particulate filters to have this test data, third-party test data. And what it say is that you basically tested your filter under a set of conditions in a duct for different particulate size. We talk about between 0.3 to 1 micron, 1 to 3 micron, and 3 to 10 micron, the bigger size. And then depending on your result, you rate your filter. To put things into perspective, today in commercial buildings, we have MERV 8, 7 or 8. And 7 or 8, they don't have any ratings for small particles, 0.3 to 1, it can be whatever. But then they have for range 2, range 3. So the efficiency, average efficiency between 1 to 3 micron should be more than 20, between 3 to 10 should be more than 70. And also for MERV 13, this is basically the efficiency. So when you buy a MERV 13, they need to have this minimum efficiency. And note my word here is very important. This is a minimum efficiency. So you can have a MERV 8 that have efficiency, the small particle size of 20, 30. And this is what you know when you take a look at the actual report. So when we say the recommendation is MERV 13, we're saying a filter that have this characteristic. This graph show you efficiency. You have to multiply by 100 versus different particulate size. And I want to put this here on purpose because you basically will have an idea of how efficiency curve work. And I don't know if you know this, but HEPA are rated at 0.3 micron. So you're talking here, somewhere between here. And it's not because they don't work below 0.3 micron. The reason is that most filters are least efficient at this 0.3 micron. And has to do is that the filter is not a sieve, it's not a sheet that certain size go in, certain size don't go in. It's much more complex mechanism between diffusion, impaction, interception. And this is how, if you have a filter, this is how the way it will work. So the least efficiency would be between like 0.2, 0.3 micron, and this is where some filters are rated specifically at this size. So, okay, so we have MERV filters. We know how filters work and the different mechanism. We have a chart. Now, how can we say which filter will work the best? There's one more piece of information that we needed to know. What is the size of the virus that we basically, when we breathe, when we sing, when we talk loudly, what do we emit? What size do we emit? And also the other thing is that what is the distribution? Like when we talk loudly or when we cough and sneeze, what size distribution? So what are the different percentages in the sizes that we breathe? This is really important in understanding later the efficiency of the different filters. So here it is. I'm going just to show you. So basically, there's a lot of studies out there, fortunately, that study different type of virus and emission from breathing, singing, talking, etc. And what they found is that, which is very good news, is that our emission from viral load and from viruses is not very small. It's actually 35% is more than 4 micron. And 42% less than 1 micron. But here's the catch. If you were actually to look is that when we do these different activities, 90% of our emitted particles will be less than 1 micron. But if you talk about the viral load, only 40% of the RNA, so the virus, is less than 1. The rest are above 1. And this is good news because it means even MERV 7 or MERV 8, today what you have in buildings, have some efficiency. And here are the results. So there's a lot of math and equations that went through this and a lot of studies, but here's an example of results. So if you want to ask, okay, if I have MERV 7 or MERV 13, what does it mean? What does it mean, the efficiency specific to the virus or specific to PM 2.5 or PM 10? So specific to it, you can see that MERV 7 or MERV 8 is a little bit more, have efficiency of 44%, MERV 11, 72%, MERV 13, 87%. And this is average over a lot of different, filters. I will show you later in the next few slides some detail. But what's really important is that the message and takeaway from this is that there is good news here. Even MERV 7 and MERV 8 will have some efficiency to protect us from COVID, and MERV 13 have efficiency like 87%, depending on the filter, as I will show you a little bit later. To get these numbers for yourself, you can go ask the manufacturer for the third-party 52.2 test data and have yourself look at these specific efficiencies. So, and this is, to recap, when we select a filter, you have to basically be aware of the energy consumption, of the pressure drop, and removal efficiency. We talk about pressure drop. If today you have a 2-inch filter MERV 7, it might be feasible or not feasible to upgrade to MERV 13 and not restrict or choke the flow, depending on the choice of your filter. Also, the removal efficiency is important, as I showed you, because I will show you a little bit later. Let's dig deep into it. So what I'm showing you here is 2 myths regarding particulate filtration. Myth number 1 is, I hear this a lot. Oh, we cannot put MERV 13. We can't upgrade our filtration because we can't, like our system will choke, we'll have too much pressure drop, and we will not be able to basically, we'll have less airflow, etc. But if you look actually, let me put myself here. If you look at this graph is pressure drop on the y-axis, and all of the filters are on the same, basically apples to apples phase velocity. And this is the MERV, which is the rating of the filter. This is from a database of 120 filters that exist today on the market. So 120 filters from different manufacturers, from their own test data reported by a third party. And what I want to show you here, like a quick takeaway, is that you can purchase a high efficiency filter, MERV 13, that have a low pressure drop or lower pressure drop than MERV 8. So this is myth number one, is that it's not necessarily if you have a high efficiency filter that you will have a higher pressure drop. But to know this, you need to actually look at the third-party test data. Second myth is that if you just installed MERV 13, it doesn't tell you or tell me what is the efficiency. So here you need to take care of actually calculating the efficiency or deriving it from the third-party test data. There's a quick way to do it based on the size distribution. But to give you here a quick example, here is efficiency, and this in this case PM 2.5. So particulate matter less than 2.5 micron. And this is the pressure drop. You see in green, those are all MERV 13 filters. But as I note here, MERV doesn't necessarily equal MERV, as you see. So you can pick a MERV 13 filter that have an efficiency 55% or have an efficiency of 80, basically 85, 82%, whatever is the number on that chart. So it's really important if you want to do a performance-based approach is to actually look at this test data and know what you're actually buying from pressure drop and from efficiency. That will dictate your energy consumption and also your indoor air quality. And you will have these slides later. I know I'm going, fast through them, but you will have these slides later if you want to check, the different numbers. The last I have around filtration is bypass. So bypass, it means that your filters are not very well installed. And there is air going through, between two filters or on the side of the filters. So this air is going through and not getting filtered. And this is really important. In the different societies or organizations, we say, be careful about filter bypass, make sure your filters are well installed. But then, you need to understand the magnitude or the effect of bypass. And I started looking at this when I saw a paper that did field measurements in a hospital. And they had a very good two filters, MERV 10 and MERV 15. So it's a hospital, should be very, very good filters. But then the researchers were able to measure the virus on the supply damper. So the virus somehow was able to be, to go to the HVAC system, go through two very good filters, MERV 10 and then MERV 15. I started thinking why is that? Why did the virus were found on the supply? So we are recirculating the virus in the space. And the reason being is bypass. So there is a research, and I apologize, I don't have the reference. I will make sure to put it before I send you the slide. There's research from Professor Jeffrey Siegel. He used to be a professor at University of Texas at Austin a few years back. But basically what they did and what the table show you is that if you have bypass, and look how much, a very tiny bypass, 1 centimeter. And if you have a MERV 15, which is very, very good filter, it will act as a MERV 8. So what does it mean it will act as MERV 8? So because MERV 15 in this case had higher pressure drop, so the air is always going to go through the path of least resistance, and they're going not to pass through the filter itself, it's going to take the cracks, in this case, this 10 millimeter, very, very small crack, and go there. And as a result, if you look at the aggregate result, it's going to act like MERV 8. So this is really important because if you invested in a MERV 15 or MERV 11 or 13 or 14, it doesn't matter. You paid supposedly more money. And maybe you had, you're consuming more energy, and maybe you had other negative consequences, but then your resulting is that you're not benefiting from, COVID perspective or indoor air quality perspective. So I cannot stress this enough to take care of your bypass, either in commercial building or actually in your residential house. In my house, I use blue tape and duct tape everywhere. So I have basically all the filters sealed. So that was about filtration. My next topic is about coil cleaning. I have a few slides here. And in the coil cleaning, I'm going to talk about the traditional methods and also about ultraviolet, so UVC or UVGI. So why do we even do coil cleaning? Coil cleaning is required in the standard for you to have a building that's compliant. So you need to do coil cleaning, you need to check your coils and your drain pans. And myself, I didn't used to look at coils. I used to stop at filters. But now I'm, working in this, so I can see the different disasters, if you want, on the coils. Specifically, if you have an environment that is, have a lot of people, or a hospital, or a food court, or a food plant. So it's commercial buildings if you have a lot of people in them. And imagine this, like all our air in our HVAC system pass through coil, whether cooling coil, heating coils, other type of heat exchangers. This is a choke point of every single system. It can impact your energy, air quality, and also in this case, if you have a coil that's blocked, it can lower your airflow, which is counterintuitive. What we're trying to do is to increase ventilation, and this will lower it. There is a lot of research out there that talk about that coils can disseminate contaminant back to the airstream. There's another research that is very well thought after. They use the largest indoor air quality database ever collected in the United States. And it's a combination of different universities, including Harvard Public School of Health, Lawrence Berkeley Lab, and EPA. And they said basically is that you need to clean your coil frequently, more frequently than 1 year. And this research say that if you only clean it once per year, rather than to do it twice or more frequent, you're gonna have more headache, eye symptoms, lower respiratory symptoms, and fatigue, difficulty, concentration. So all of this, I mean, we know indoor air quality is important, but here is, highlighting coil cleaning. So what do we mean by that? So we have some goals when we want to do coil cleaning. This is, a lot of information, but basically follow me here. So coil cleaning goals. The first one is we want to remove the biofilm. So everything that's stuck on the coil, dust, bacteria, mold, fungi, spores, whatever you want to call them, the terminology, is to remove them from all the depths of the coil, not only from the surface, from all the depths on the coil. And the second goal, which is really important, is to not re-aerosolize. If you have something on the coil, you don't clean it by just putting it in the airstream and put it back into the building. So this is why traditional cleaning methods, for example, pressure and steam washing, are not recommended. And here I put I need to put the link from ASHRAE, but if you go to the ASHRAE commercial guide, it will say it's not recommended to do pressure and steam washing because you are re-aerosolizing the particles back into the airstream. The other thing is about UV. So UVC and UVGI, they surge in sales, specifically during the pandemic, in places other than healthcare environment. And I put here a link about a new article that it was newly published by FDA, and it was reiterated by CNN. Basically, it says, the UV might be limited to remove the virus. And here's an explanation of it. What do they mean by that? On the right-hand side, where I'm putting my cursor, left-hand side, this is a project that was funded by ASHRAE Project 1738 in University of Pennsylvania. What they do is they went to a university, University of Tampa, and they basically did measurement and verification before and after applying UVGI, so UVC. So the picture on top is before they started, and the picture below is after 13 months. And you can see that, UV is not the magical bullet that you put it there, it's gonna shine a light and kill everything and restore the coil back to its original conditions, because this is a way that's being sold. UV is a good idea if you know what you're getting yourself into it in terms of, different parameters. And here, there's much more to it, but here's like a brief summary. So if you are interested, you can go and look at the different points. The first one is direct exposure. The way that UV works, it has to have a direct exposure on the specific virus on the surface of question. So if you have the virus that have fluid or you have dust, it's not gonna remove it. And by that means, it's not gonna clean your coils from other bacteria and spores. The second one is dose and duration. And this is really extremely important. I did a lot of digging, and I couldn't find that manufacturers are actually publishing the dose. Dose, it means the light intensity, which is a critical #1 factor is how much I'm cleaning. And they are expensive. I saw some quotes from different manufacturers, and they are expensive for what you get, for the dose that you get. So my advice here is that if you're purchasing, speccing UV for your house, your building, healthcare, you need to understand the dose and the light intensity so you can basically understand this light intensity, how much efficiency of the virus removal you are getting. The third one, I've seen this a lot, that UV is marketed to remove on the fly. On the fly, we remove the virus, bacteria, spores. That's not actually true, because you need certain residence time for UV to remove basically the contaminant in question. For example, if you put the UV lamps after your cooling coils in the HVAC system, you don't have any effect on the fly effect for bacteria and spores. We know the science. You can do simple calculation. You can see there's no effect on the fly effect again. Then there are some other parameters, and those are well documented in different standards. Loss of output is one of them. Like most of the application of UV in the duct or in the basically HVAC system is after the cooling coil, where the temperature is low. It's 55 Fahrenheit or something like that, 55 to 60. Well, guess what? That if you have a temperature that's cold, you're gonna lose a lot from the intensity of the light, up to 55%. Again, this is not information that's proprietary. Like, you can actually look at this information in the ASHRAE standard, how to spec UV. Other one is depreciation throughout the life of the lamps. Surface loss is another very important one. Is UVC will degrade organic material. So it will degrade filters, wires, etc. So you need to spend and be careful. When you retrofit your HVAC system with UV, there's a lot more consideration that you need to take into account. The other one is safety. So I will leave it at that. There is CDC and EPA website goes in details into the safety, skin and basically eyes. And also one more thing is that you need to consider the total, life cycle cost of owning UV, changing lamps and other different, maintenance. So the one strategy that is recommended, and again, you can see it in the ASHRAE commercial guide, is to do an enzyme-based technology. So, and I like to say this, I don't know how accurate it is, but like a shaving cream. So in a way that you don't re-aerosolize particulate back into the airstream, but at the same time, you go through the depths of the coil. So you put this enzyme technology before, and actually you see a total breakthrough after. So this is before, and this is after. This is the only way that you can ensure that you have an instant coil cleaning, and you restored your coil back to the original design conditions, basically original pressure drop, if you can measure before and after, pressure drop and airflow. And this is what I was talking about before. If you have this situation, then, and if you have a fan that you cannot regulate your airflow, then in this case, you're gonna have less total supply, less supply airflow. It means you have less ventilation. So this is, counterproductive if you increase your ventilation. Another way to do it, instead of increasing ventilation, if you have this case, is just to clean your coils. If you clean your coil, then you will have more ventilation air that you lost before. And perhaps if you clean your coil, you can remove some of the pressure drop and you will be able to put a better efficiency filter. Okay, so the last item here is about flush out. Before I show you the modeling results. Do you have any questions? No. Okay, so flush out. Flush out refers to bringing outside air to your building before occupancy. Usually we don't do this. Usually we have our ventilation system controls just start when basically people come to the building. So flush out, if you have a LEED building or a different green certification building, maybe you already have flush out. But what's important, and I saw a lot of questions about this, how much should we do flush out and how much outside air? It's very important to say that flush out, it doesn't mean that you need to have 100% outside air. It doesn't mean that. It means that if you have certain quantity of outside air, then you need to have a minimum number of hours that you can do the flush out. And you can distribute it based on your certain consideration. So let me run you through this quickly. On the y-axis is the time of flush out, so duration in hours. And on the x-axis is how much air exchange rate you have. So how much ventilation air you have you divide by the volume of your space, you get air exchange rate. And then ASHRAE recommendation is to follow the orange line, which means that your indoor concentration is reduced by 95%. So imagine you have people in the building from 8 to 5. 8 to 5, they leave. Then in preparation for the next day, you want to make sure that you remove 95% of the particulate in your space. So this is the orange line. If you have one air exchange rate, you follow basically one air exchange rate, you need to do flush out for 3 hours. How you do 3 hours? You can do them after 5 p.m., at night, you can do them in the morning, it doesn't matter. It's your choice, and you can choose it based on outside air temperature, like on your demand, and on other factors. Likely that will happen in the morning will be better. Now, some guidance say do 4 hours, but where did the 4 hours come? It really depends on how much outside air you have and how much flush out you have. Typically today, the minimum in commercial building, you will have 0.7 air exchange rate. This is a minimum. So you have here, if you don't go above the minimum, so you need around 4.5 hours. Again, you can distribute them, these hours, basically like you want. So this is another thing is important to understand, so you can balance the cost. You don't have to have 100% outside air, and you can choose when to actually do this. Okay, so I talked to you about different strategies, and I talk a little bit about how to rank these different strategies. At the end of the day, you need to make a decision, and your decision can be driven by doing a risk infection model and then put cost and balance those out. I'm going to show you a quick example here, and you can repeat it for different strategies, including wearing masks, for example, or putting a portable air cleaner, etc. Today, I'm going to show you the simple one, which is filtration and ventilation. Those two are already existing in your building, and you can decide what to do. So this is a Wells-Riley infection model. It's basically a model that tells you the risk of infection, so probability of infection. And it has to do mainly with the airborne infection. So it assumes that people are socially distant from each other. Basically, it assumes the 6 feet is maintained, and here is only about airborne risk. And what does this model say is that you have sources and losses. The sources are infected people, and also how much duration you spend in the space, and how much you're breathing and your activity. If you are in the gym, it's going to be very different if you are in an isolated room and sitting down quietly or sleeping and not talking. And then here we talk about ventilation, filtration, and other parameters, including the virus decay. So I'm going to focus today about ventilation and filtration. Show you directly the results. This is a risk infection model run for an office building, 40,000 square feet, and 200 occupants. On the y-axis is the risk of infection. The lower, the better. And the x-axis is the outdoor air exchange rate, ventilation. And then for the different series, different colors are different filtration level. So this is combined together, risk of infection, different filtration level, and different ventilation level. So one of the guidance say, increase outside air as much as possible. Well, as much as possible in this case, it means, we're talking about here, air exchange rate of 6. It means 100% of your outside air, of your total supply to be outside air. So your whole air is outside air. That's not likely feasible in many of the buildings, but it's one, assumption that you can open, like all your supply air is outside air. So you're here. And you can see that if you have 100% outside air, as I mentioned at the beginning, it does not matter what filtration you use, because this filtration specifically is for indoor air. Filtration is always a good idea, but here we're talking about COVID-19 pandemic situation. If you have 100% outside air, so you are here, it does not matter what filter you use. Today in buildings, most of them are here. And this is VRP, it means ventilation rate procedure. This is the minimum to be compliant. So the minimum to be compliant is this line. And you see here, if you use the gray, which is MERV 13, so if you are at this point, it doesn't matter much how much outside air you have. So that's why some of the new guidance from ASHRAE say your basis is MERV 13 and minimum outside air. So this point, rather than to be this point or a different point. Because if you have MERV 13, it doesn't matter a lot from infection risk to add your ventilation. And I think this picture will put everything I said together and will explain it. We have Houston, we don't have Austin, but the climates are similar. So this is the infection risk on the y-axis and the cost. The annual cost includes like labor cost, includes operating cost, and also the cost to purchase a 1 CFM of outside air or a filter. So these 4 charts here, green, blue, black, and red, are ventilation. And the purple is filtration. You directly see big level, like high level. Filtration has lower cost than ventilation. And if you have MERV 13, or even MERV 11 or MERV 13, 14, you can achieve a very similar infection risk than increasing your ventilation. So this is important, and put this in context. Have many more slides about specific if you increase your ventilation by 10%, 20, 30, or all the way to 100. But I want to put this picture to show you that filtration is cheaper than ventilation, specifically if you have a climate that's hot and humid, like Houston, or hot like Phoenix, Arizona. Okay, this is my last slide, and thank you for staying this long and listening to me. My last slide is about COVID-19 testing. So before the pandemic, we basically have on the market a lot of sensors that measure air quality. Some of them directly, some of them indirectly. An example is carbon dioxide sensors. So carbon dioxide sensors, we have cheap sensors. They're fairly sort of accurate and reliable. If you take care of them, you need to do the calibration. But basically, you can use carbon dioxide sensors to give you an idea of how good your space is ventilated. There's ozone, there's particulate matter. So it gives you an indication of, okay, how good is your filtration system, ventilation, etc. But here in this, and you still can deploy those and trend them, and even trend outdoor air pollution and take sort of performance based to what your system should do. But this specific, I want to talk to you about COVID-19 testing, like direct COVID-19 testing. And this is not about human testing. I'm talking about space or air. So I have two set of tests. On the left set is swab test. So this is surface testing. And this is you can do in your HVAC system. You can swab your coils, ducts, fans, filters, or you can do it in your space, like a desk, a monitor, or like door handles, like the most surfaces, elevator buttons, etc. And this test can tell you if you have a presence or absence of the virus, and can tell you actually as well concentration in the specific area that you swabbed. It doesn't tell you infectivity, so this is important. So absence, presence, and concentration. Similar, you have air sampling. I'm very big fan of air sampling because air sampling can tell you if all your strategies combined, including source control, mask, social distancing, reducing occupancy, and all the other HVAC strategies, if they are working. So air sampling, it involves a pump, a filter on it, you run it for a specific amount of time, and then you have these filters and you send them to the lab and can tell you the same thing, concentration, presence, or absence. And this is one point in time, it's true, but some people and industries are using it as an assurance, from liability purposes. In this point of time, with all these strategies in a typical day, we measured and these were the results. And this is something also people can opt to do if you have a COVID-19 test and you did strategies and you want to reopen. This is like another add-on strategy to do. And thank you. That was my presentation. I think I stayed on time. Let me know if you have any questions.
Yeah, Marwa, I put a question in the chat box. But basically, how do those infection models change when you have higher density occupancies like a school classroom?
Yeah, So it's a very good question. So in the model, you can do two ways. The first way, you can say that this is the total occupancy, and we call them the susceptible population. So let's say in your classroom, you have 100 kids, and then you estimate how many infected kids. So this is an assumption that you make, 2, 3, 4, etc. And then at the end, you obtain basically an infection probability. And this infection probability you apply to your population. Another way to do it, which is, it might be, a little bit better and more accurate, is we look at the county. So today I'm in Austin, I'm in Travis County. I look at Travis County and I see how many people are infected or hospitalized or death per 100,000 people. And I can apply this at the model, taking the total number of kids in the classroom. It's, common sense is that if you have less occupants, you will have less chance to have an infected person. And if you're not there, you're not going to get impacted. And the model can address this. Like you can have the model exact same parameters, but instead of like 10 kids in the classroom, you can have 5 and you can see the difference of infection. I can read the other question. Is from Cliff. If you were to propose virus mitigation for a large building, what's the first step to take? Assume the building has 100 air handling units, have outside air, and some do not. How do you know what strategies to propose? Seem like a walkthrough survey is needed. So this is a very good question. And I'm more like optimistic than other people. And my first step to take is to make sure that the basics are there. And I'm talking about the basics of what we know, how we should run a building. And what do I mean by this? The 3 most important recommendations is ventilation, filtration, and coil cleaning. And I would start my basically survey to make sure that those are met per the minimum standard that need to be compliant. And those what we call today tactical commissioning. So it's not a full commissioning of your building, it's tactical commissioning of some components and then systems to think, okay, is my building ready? Do I have this specific? And then after that, I go into upgrades. And my basically spiel into the upgrades is basically to be also tactical about them. So between, for example, opening your 100% outside air or using MER 13, I would go to MER 13. Now, we all understand that to fight this pandemic, we need to do a multi-layered defense strategies. And I'm giving you the 3 most cost-effective, and today you have them in your building. Ventilation, filtration, coil cleaning. Now, if you have a building or a space like a theater or the nurse's office, or you have a university that don't have ventilation altogether, they have the window AC unit, you can even do filtration. In this case, you can go one step further and add a portable air cleaner. But the portable air cleaner will follow the same logic. You don't need fancy ions, UV, etc. Focus on having a portable air cleaner with high efficiency, high enough of a volume, so airflow and efficiency. And there is a specific guidance about this, what is the combination of efficiency, airflow that you need to have for a specific area. And ASHRAE does a great job in that. If you go to the ASHRAE building readiness, so ASHRAE COVID-19, and there's a building readiness chapter, you can go through it and do this, basically. If I didn't answer your question, let me know. I can go into more details.
Well, I think we have time for 1 or 2 more questions, if anybody has that. We've got about 3 minutes to 12:30. So we'll hang on a second, and if we don't have any more questions, we'll wrap up. Okay, well, I'll take that as we have no more questions. Thank you so much, Marwa, for this great presentation. It's clear you're very knowledgeable in this subject, and this is very timely and useful material that you presented to us today. So I want to thank you very, very much. And I know that our attendees have gotten a lot out of this.
Thank you so much, everyone. I know this was a lot of information. I'm going for sure to share my presentation. I'm going to add the references really quick so you can read further on it. And I look forward to, since I moved now to Austin, to meet everyone in person. Thank you so much and have a great day.
All right. Well, thank you. This wraps up our August meeting of the Association of Energy Engineers, Austin San Antonio chapter. Thank you and have a great rest of your day.
Thank you, everyone. Bye-bye.